Hello again. Today we're going to be talking about improper integrals and how to use L'Hopital's rule with them. So first, let's remember the first fundamental theorem of calculus. So normally when we evaluate a definite integral, we just find the antiderivative and we plug in the endpoints and we simplify. Okay, we've done that before many times. So what if the integral is improper? And what that means is one of your endpoints is infinity instead of a constant. So I still do find the antiderivative. So I'm going to find the antiderivative of x to the negative 2, but what do I plug into it? I really can't plug in infinity. That doesn't make sense. So what I have to do instead is I have to take the limit as b goes to infinity. So what I do is instead of using infinity, I set up this constant b and I let b go to infinity and treat it as a limit. So that gives me the limit as b goes to infinity of negative b to the negative 1, which is what I get when I plug that b value in, minus whatever I get when I plug that 2 in, which is just negative a half. I don't need to use a limit for that because it's just staying at 2. It's not approaching anything. All right, well, as b goes to infinity, negative 1 over b is going to approach 0. So all I have is negative a half, which is just a half. All right, looking at another example, I'm going from 2 to infinity of e to the negative x. So again, I take the antiderivative of that, which is negative e to the negative x, and the integral will now go from 2 to b, and I will let b go to infinity. Okay, and so if I plug that b value in, I get negative e to the negative b. Minus, if I plug in 2, I'll get negative e to the negative 2. But remember, I have to take the limit as that b value goes to infinity. As b goes to infinity, that's going to go to 0 as well, and I'll just be left with negative e to the negative 2, which is just 1 over e squared. All right, well, sometimes the integral diverges. If I'm going from 4 to infinity of 1 over x, okay? So that's going to give me the limit as b goes to infinity of the natural log of x, which is the antiderivative of 1 over x. And I'm plugging in b and I'm plugging in 4 and I'm letting b go to infinity. So that gets me the limit as b goes to infinity of the natural log of b minus the natural log of 4. Well, unlike the other examples, the natural log of b is not going to approach 0 as b goes to infinity. It's actually going to approach infinity as well. So this integral diverges. There is no constant that this integral is equal to. So it goes to infinity. All right, so here's an example where the integrand has an infinity discontinuity. So if I'm going from 0 to 1, and the function is 1 over the fourth root of x, well, the fourth root of x doesn't actually, or 1 over the fourth root of x doesn't actually exist at 0. It's undefined. So what I have to do is I have to create a b and let b approach 0 from the left hand or from the right hand side, and see what happens there. So I, first of all, I plug in 1, and that's easy enough to do. I'll get 4/3 times 1 to the 3/4, but then I'll have to take the limit as b approaches 0 from the right-hand side of 4/3 times b to the 3/4. Luckily, that does approach 0, and I'm left with just 4/3 as my answer. All right, now what if the limit is indeterminate? So let's say I'm going from 1 to infinity of x times e to the negative x. Well, I'm going to have to do integration by parts with this, which I've talked about before. So my dv is going to be e to the negative x because that's an exponential, meaning that my u is just going to be x. So I work through the table. The derivative of x is 1. The antiderivative of e to the negative x is negative e to the negative x. And if I keep going, the derivative of 1 is 0, and the antiderivative of negative e to the negative x is back to e to the negative x. So my answer is x times negative e to the negative x. But remember, I'm going from 1 to infinity, so I have to go from 1 to b and let b go to infinity using a limit. The next term is going to be negative 1 e to the negative x, again from 1 to b, letting b go to infinity. And then the last one, because I'm reading across the row, that's still going to be an integral from 1 to infinity, but the integrand there is just 0. So that actually works out to be just 0. All right, so here I'm going to plug in b first and get the limit as b goes to infinity of negative b over e to the b. And then when I plug in 1, I get 1 over e to the 1. And for the second one, I'm going to take the limit as b goes to infinity of 1 over e to the b. And then when I plug in 1 into that second one, I get 1 over e. So that's what I get. I'm just going to change that negative to a positive and change the signs of those things in the second set of brackets there, just to make it easier to work with. As b goes to infinity, that 1 over e to the b is going to approach 0, so I don't need to look at that. And now this limit becomes the negative limit of b over e to the b. And then those two 1 over e's that I have can simplify to be 2 over e. But now I'm looking at this limit of b over e to the b. Well, that's indeterminate. As b goes to infinity, both the numerator and the denominator go to infinity, which means I need to apply L'Hopital's rule. So the derivative of the top is just going to be 1, and the derivative of the bottom is going to be e to the b again. So now I can find the limit of this. It will not be indeterminate again. It will actually be 0. So my answer will simply be 2 over e. All right, another example. Let's say I have the integral from 0 to pi of this expression right here. I'm going to use integration by parts again. And the numerator is going to be my u, and my denominator, which I'm going to write as x to the negative 2, is going to be my dv. Take the antiderivative, or take the derivative of that u value, and I get negative x sine x. And then the antiderivative of x to the negative 2 is going to be negative x to the negative 1. And so now I'm ready to write my answer as the limit of sine x minus x cosine x all over x. I kind of divided out the negatives there, canceled them out, so I could write it more simply. And then across the bottom row, that still has to stay as an integral there. All right, so that can be rewritten as the limit of sine x over x minus the limit of cosine x, because those x's in that second fraction canceled. So I'm just left with the limit of cosine x. All right. And now I still have that integral at the end, which is x sine x over x. I just simplified that to be sine x dx. All right, I'm going to copy those first two terms and find the antiderivative of that, which is just cosine. I'm taking the limit from b to pi. All right, so let's continue on. I have the limit as b goes to 0 of sine x over x. I'm taking that limit from b to pi. So that's going to be the sine of pi over pi minus that limit of sine x over x. Well, that sine x over x is indeterminate because I'm going to get 0 over 0. And so I use L'Hopital's rule. I'll still get sine pi over pi minus the derivative of sine x is going to be cosine x, and the derivative of x is going to be 1. If I plug 0 into that, I don't get indeterminate anymore. I don't get 0 over 0. Instead, I get 1 over 1. Sine pi over pi simplifies to be 0 over pi, which is just 0. So my expression ends up being negative 1. So that's how you would use L'Hopital's rule for improper integrals. We're going to get a lot of practice on that. So if you have any questions, please let me know, and I will see you tomorrow.